In this lecture, we'll talk about properties of skew-symmetric matrices and the hat operator, which we saw in the expressions for angular velocity. First, let's define an operation called the matrix transpose, denoted by the superscript T. Let A be an n by m matrix, and let A, ij denote the element in the ith row and jth column of A. The ijth component of the transpose of A is the jith component of A. Loosely speaking, the transpose operation flips the rows and columns of the matrix A. Consider the following 2 by 2 matrix. The transpose of this matrix swaps the terms in the 2, 1 and 1, 2 positions. Note that the diagonal of a matrix always remains unchanged after taking the transpose. Consider the following rectangular matrix. The transpose of this matrix looks like this. Notice how, for rectangular matrices, the dimensions of the transpose is different from the dimensions of the original matrix. In this example, the original matrix is a 2 by 3 matrix. The transpose becomes a 3 by 2 matrix. Consider the matrix that is the result of the previous problem. The transpose of this matrix is calculated here. Notice that we get back to the original matrix from the last problem. We see from this example that the transpose of A transpose is A itself. Finally, consider the 1 by 3 matrix, which is simply a row vector. The transpose operation turns this row vector into a column vector. We say that a matrix A is symmetric if A transpose equals A. We say that a matrix A is skew symmetric if A transpose equals the negative of A. Let's consider specifically 3 by 3 skew symmetric matrices. Consider an arbitrary 3 by 3 matrix A. Using the definition of skew symmetric, this matrix is skew symmetric if the following expression is satisfied. Matching up the components of the two matrices on either side of the expression, we get 6 constraints that must be satisfied for A to be skew symmetric. We see that the first 3 constraints say that the components A11, A22, and A33 must equal the negative of themselves. The only scalar that satisfies this criteria is 0. We see that a skew symmetric matrix must have all zeros on its diagonal. The last 3 constraints relate the remaining 6 components of the matrix. Substituting these constraints into the matrix gives us the following general expression for a 3 by 3 skew symmetric matrix. In particular, notice that because of the constraints for skew symmetry, this matrix only has 3 independent parameters. As a result, we can concisely represent any skew symmetric 3 by 3 matrix as a 3 by 1 vector. The hat operator allows us to switch between these 2 representations. Explicitly, A hat, where A is a 3 by 1 vector, is a 3 by 3 skew symmetric matrix defined by the 3 components of the vector A. For example, consider the vector omega equals 1, 2, 3. The corresponding skew symmetric matrix omega hat is shown here. The hat operator is also used to denote the cross product between 2 vectors. That is, u cross v can be written as u hat times v. This means that the cross product of u and v is equal to the skew symmetric matrix corresponding to u multiplied by v. For this reason, the skew symmetric matrix corresponding to u hat is sometimes denoted as u cross. In lecture, we defined the following 2 angular velocity vectors. Will these angular velocity vectors always exist? Recall that we proved that R transpose R dot and R dot R transpose are both skew symmetric matrices. From the properties we derived earlier, we then know that we are guaranteed to be able to find angular velocity vectors omega b and omega s that satisfy the given definitions of angular velocity.